and get that current slide. Okay. Now, announcements. I think I told you all before about Alabama A&M University having the North Scholarship Program. I can't recall if I said this to you or not, but when I first introduced it, I said the one they had at UAB and the one they had at University of Alabama both had summer programs, and they paid students to come, and it was the thing. From what I understand, A&M isn't doing any of that. They just pay tuition the last 2 years, okay, which is great. It's a good deal, but you have to basically, there's no teasers out there trying to get you to come. You just have to show up and apply and show up. All right. And I think that was the only one I had there. Okay. So, any questions on anything we've done so far? All right. We picked up then, we left off in 10.2, and I think we finished the second example on page 702. Oh, yeah, you may have. Yeah. Okay. And I think we did the second because I have my mark at example 3, which doesn't show up in the slide set, but it is at larsoncalculus.com. And you can go there for an interactive version of that example. So let me see. Okay, I think this is the best I'm going to be able to do right here for space for example 3. Using trigonometry to eliminate a parameter. So it says sketch a curve represented by x. Oops, let me get my pen set up. X is equal to 3 cosine theta. And y is equal to 4 sine theta. Okay. And we're going to do this parameterization by 0 less than or equal to theta is less than or equal to 2 pi. Okay. It says sketch the curve represented by these two by eliminating the parameter and finding the corresponding rectangular equation. So rather than taking thetas, which you could do perfectly fine, theta equal 0, theta equal to pi halves, theta equal pi, theta equal 3 halves pi, you could plot those points and get a good idea of what this is going to look like. However, they're saying do this one by eliminating the parameter and finding the corresponding rectangular equation. Okay? Now, to eliminate the parameter, here's what I would try first. I'm not saying it will work. I left off my 3, didn't I? I think I said it and didn't write it. X is equal to 3 cosine theta, y is equal to 4 sine theta, and theta between those two. Ooh, where my brain is, I don't know. All right. So, I would be real tempted to try this right off the top. Divide the second equation by the first equation, just to see what happens. Okay, well, no, that's not really going to help that much, I don't think, because it says eliminate the parameter. I was going to get it into tangent theta, which would be okay too, but that wouldn't eliminate the parameter. All right, so I guess what they're requiring or requesting us to do is first solving this for theta, which at first is solving for cosine theta. So cosine theta is equal to x over 3. Divide both sides by 3. Okay? And then do theta is equal to inverse cosine of x over 3. And then plug that in here. And you know, rather than doing this, I'm going to draw a triangle. I like drawing triangles, okay? I'm going to draw a triangle here, and supposedly that's a right angle, okay? And this will be my angle theta. This may not help either. Sine of theta is 4 over, I'm sorry, over y. That's not going to be helpful, okay? Because normally it's opposite over hypotenuse, and your y is that. But we could call this y for now, for lack of anything else. And cosine theta is x over 3. No, I said that wrong. Sine of theta, no, that's right, is y over 4. Sine theta is y over 4. So y over 4, okay? But then if you did cosine theta is x, this x, over 3. In other words, you come down 1 from there. Now, I don't know, this is not particularly helpful looking either, I don't think. No, that doesn't look like it's going to make anything any better either. I was hoping it would, but it won't. Okay. Let's see, go on what I was doing before. Y is equal to 4 times the sine of the inverse cosine of x over 3. Now, does that help us in any way? I can't really imagine either one of these making any sense here. Okay. Well, here's what I was going to do in the first place. I didn't think it was going to work, but now I'll try it. Forget all that. Okay. I really did think about that we could use Pythagorean theorem here. Well, wait. Let's do that. Don't erase everything, but let's erase some of it. Yeah. Cosine theta is x over 3. Sine theta is y over 4. And then we know that sine squared theta plus cosine squared theta is equal to 1. Don't we know that? Okay. Well, sine squared would be y squared over 16 plus x squared over 9 is equal to 1. Okay. Remember what we did in just going through that first section of this chapter? This forms an ellipse whose major axis is the y-axis and the minor axis is the x-axis. Okay? Now what we're supposed to, by eliminating the parameter and finding the corresponding rectangular equation. That's what it would be. And that would be, if I'm not mistaken, one lap around the And you can start it wherever you want to, but it would be the ellipse. Whoops, I didn't go up high enough. Like that, and like this, and like this, and like that. Pretty ugly, but you get the general idea. Drawing in this form, though, you lose the directional characteristic of it. Okay? If you go back to the original here, when theta is equal, in terms of theta, when theta equals 0, where are we? X is equal to 3 cosine theta. Well, theta equals 0, cosine is 1, so that'll be 3. There we are. And y, of course, is 0 because sine of 0 is 0. And if you go up to pi halves, then cosine goes to 0 and sine is at 4. So you're here. So this is the direction you're going. What my gut feeling was telling me that would be one loop around the elliptic track. Okay. And mine doesn't look very pretty because I've got this too. Yeah, something like that. Okay. So it would be counterclockwise from 0 to 2 pi, starting at 3, 0, going up next to 0, 4, and continuing all the way around. Okay. Using the technique shown in this example, you conclude that the graph of a parametric equation, so here's another little added at the bottom, x is equal to h plus a cosine theta, and y is equal to k plus b sine theta. Okay, b sine theta, yeah. When theta is 0 to 2 pi. Okay. That basically you'll be an ellipse whose center now is not at the origin but is at the point hk. H for x and y for k. So that equation would then be something like this: x minus h over a squared, x minus h squared over a squared, plus y minus k squared over b squared is equal to 1. Okay. Yeah. Now, it's said that in examples 2 and 3, the eliminating the parameter is primarily to aid in curve sketching. When the parametric equations represent a path of a moving object, the graph alone is not sufficient to describe the motion of the object. You still need the parametric equations to tell you position, direction, and speed at a given time. You can't get that by going to eliminating the parametric equation. So that leads to, well, it doesn't really lead to it, but the next thing we get to is finding the parametric equations. Up till now, they've given you the parametric equations, said find the curve. Now they're going to describe a curve or do something with it, and then say you find the parametric equations. Okay? So we jump right into example 4. Find the set of parametric equations that represents the graph of y is equal to 1 minus x squared using each of the following parameters. Okay, we'll go get there in a second. But I wanted to point something out to you. Find a set of parametric equations. Just the way they word that suggests, or could suggest to you, there could be more than one set of parametric equations that could represent this, and if you did think that, you'd be absolutely right. Notice they didn't say, find the parametric equations that represent that. If there was only one, that's what they would have said. Since they said find a set of, that suggests that there could have been a variety of them. So, the first suggestion is really the simple one, what I would have gone for. they tell you the parameter, let t equal x, okay? Then that would be one parametric equation right there. What do you think the second one would be? This gives you x. What would be y? 1 minus t squared equal y. Because right there it says y is equal to 1 minus x squared. If x is t, then y would be 1 minus t squared. There you have it. Now, you can't get very much simpler than that, okay? In fact, that's usually, if they hadn't given this to you, I would have gone right for it and said, find the most complicated variable, x, let that be the parameter, and then solve the other one for that, okay? And that was already done for you here, basically. Okay. Now, here's the second parameter. Use the slope, m is equal to dy dx at the point xy, okay? So that must be going to be a parameter. M is equal to dy dx, okay? Well, let's see what we can do with that. What you reckon we could do? Here's your equation, and what would you do? Second?
You want to use like slope-intercept form?
Second.
Slope-intercept?
Okay, we're not quite there yet. We're given an equation here and told that slope is dy dx. So what do you reckon we need to do to that equation? If this were Cal 1, huh?
Should we plug something in?
No. What was the Jesus answer in Cal 1?
Oh,
take a derivative. All right. Okay. Let's do dy dx. For this, y is equal to x squared. What would that be?
2x.
Is what?
2x.
Minus 2x. Okay? All right. And the slope is m at the point xy. So so this must be m. Okay? So 2x or negative 2x is equal to m. So let's divide both sides by negative 2. And you get x is equal to minus m over 2. Okay? And let's plug that into your y. Now you can plug y is equal to 1 minus a negative m over 2 squared, which would be 1 minus an m squared over 4, which would then result in 4 minus m squared over 4. That would be your y. Rather bizarre, but okay. X equal m over minus 2, y is equal to 4 minus m squared over 4. I can't for the life of me see why they would want to do that. But that's exactly what they did. Those would be the parametric equations there. Okay. Oh, okay. So they start at m equals 0, x would be 0, but at m equals 0, y would be 1. So yeah, you start there, and then you go to the left and down for m equal 2 and stuff. If you went back the other way, the m was minus 2. So you're starting from m negative infinity up to positive infinity. That would plot you this parabola. Okay. Y is equal to 1 minus x squared. We know what that parabola looks like. In this first rendition of it, where t is equal to x, and then y would be that, and t was 0, same thing. You're starting at the same place. And t is equal to 1, that time you'd be going this way. Okay? And then minus t would be over here. So the difference between those two, they didn't show the graph of the first one, but let me, if I can, this book is not the lightest thing in the world. Okay. For that first one there, t is equal to x, whatever your x is, when x is minus t is negative, so then it would be going in this direction, from left to right. This one, however, the t is equal 0 is there, and go down this way, so negative numbers would be here. So that one starts to the right and goes to the left. So these two parameterizations both work. One goes in one direction, one goes in the other. Okay. And we've just doubled the class size. Okay. With Brian here. Okay. And we're on page 704, chapter 10, conics, parametric equations, and polar coordinates. Last week I can't remember when you were last here, but I know you weren't here when we did 10.1, which was just going over conics in general, and then 10.2 is really what you're going to be a bit more tested on directly. But we went over the conics because we're going to be using it not just here, but in a later chapter as well. So I wanted you to be exposed to it. And this is a parabolic form, what I was just holding up. The previous one had an ellipse in it. So just to recognize what those look like.
What is that? It says y equals 1 minus negative m over 2
Squared.
x.
No. Picky about my writing, huh? I understand, but I'm not at all hurt by it. No, not at all. You know.
Confused. It's all.
Okay. The x here is equal to, from this up here, solving this, m over minus 2 over minus m over 2. That was your x in terms of this parameter m. X is minus m over 2, and then plugging that in to that is what we got back.
It makes so much more sense.
Oh, okay.
I was looking at 2x equals.
Yeah. Yeah. You almost have to follow while I'm writing it, you know, because I start running out of room and it gets jumbled. All right. I think we're ready for example 5. There is first a little blurb on the left margin of 705 on cycloids. And it mentions Galileo. We think of him as one of the beginners of modern science, and he was probably more so the father of it than even Isaac Newton, because he came along one generation ahead of Newton. But he was quite a good mathematician as well. We usually think of him in terms of science alone, but he was quite a good mathematician too. Galileo first called attention to the cycloid, once recommending that it be used for the arches of bridges. Pascal, another name you might want to once spent 8 days attempting to solve many of the problems of cycloids, such as finding the area under one arch, and finding the volume of the solid of revolution formed by revolving the curve around about a line. The cycloid has so many interesting properties, it's caused so many quarrels among mathematicians that has been called the Helen of geometry or the apple of discord. Now, why the Helen, unless it was Helen of Troy, I don't know. But still not. Yeah, because I guess lots of...
Helen of Troy started a war.
Yeah, so she was, I guess, very desirable, so, or something like that. So anyway, for further information on cycloids, there's an article, Geometry of Rolling Curves by John Bloom, Lee Witt, American Mathematical Monthly, so you could report on that if you wanted to. But there's several possibilities right there. Now, half of you have gotten your paper in already, and half of you haven't, right? So just hint, hint, and for those I'm talking with, in fact, all of you have not gotten it in. All right, so let's move on to, let's see how they do it. Okay, since you were making fun of my writing, let's see if you can understand theirs better. Letting x equal t, that's the simplest parameterization, that produces for the second one, y is equal to, so this is 1 minus x squared. If x is equal to t, that's 1 minus t squared. There's your parameterization, x equal t, y is equal to 1 minus t squared in the parameter t. Okay, but then to do the other, you're right. M is equal to dy dx. That's the parameter they say to use. So, of course, you would have to take the derivative of the function, which is minus 2x. There's your parameter. Well, you need that in terms of x. I mean, x in terms of the parameter rather than the parameter in terms of x. So you just divide both sides by minus 2, and that gives you x is equal to minus m over 2. There's your parameterization for x. Plug that into your original equation, y is equal to 1 minus x squared. It would be 1 minus a negative m divided by 2 squared. But of course, that minus m divided by 2 is going to become n squared over 4 because the minus sign will disappear after you square it. And then you have 1 minus m squared over 4. So there's your y parameterization. You got your x, you got your y. Okay. Now, you can simplify that a little bit for, well, no, they left it just like that, which is fine. There's nothing wrong with it. All right. My throat's hurting. I don't know why. The cold room is part of it, but it should be. So in this figure, here's the deal. Okay. That the resulting curve has a right to left orientation determined by the values of slope m. And for part A, the curve would have the opposite orientation, left to right. Okay. If you just did the t and 1 minus t squared. Okay. Now, that was example 4. Let's see. Yes, here's example 5. Parametric equations for a cycloid. And that's why they introduced the cycloids on the little box in the margin there. Excuse me. Determine the curve traced by the point P on the circumference of a circle of radius A rolling along a straight line in a plane. Such a curve is called a cycloid. Okay? So we'll start with the parameter theta, be the measure of the circle's rotation, and let the point P, xy, begin at the origin. Okay? So, when theta is equal to 0, P is, as we said, at the origin. So theta equals 0 is when x and y are both zeros. All right. Here's Daniel. Chilled, my throat's hurting. Yeah, I don't know what's going on. So when theta is equal to 0, P's at the origin. Now, when theta is equal to pi, so we're starting with the circle right on top of the origin, and the point P is here. Okay. As the circle starts turning, P doesn't move very far, but it does lift up off the origin and begin its motion this way. So when theta is pi, so let my thumb be the initial point, and when it's turning, that's picking up, and pi would be right there, okay? So that would be, besides the broken shoulder, and here's Charles. He came to lend a hand to my shoulder, okay? And, oh, good deal, thank you. All right, the more they come, the merrier, right? All right. Okay. So then when P is equal to, when theta is equal to pi, so let's again start it here, and as it's turning, it's rolling along here, so it lifts it up there. And when you get over here, pi, where this was up here like this, now it's down like this, theta is up here. And the P is, the Y value is 2a. Remember, radius A. So here it was down here, it's rotated up until it's up here. So the Y value is 2a. Now what's the X value there? Okay. If you think about it, you went half of the circumference of the circle then, rolling along, right? And the circumference of the circle would be 2 pi a, right? So the X coordinate would be pi a, okay? And sure enough, that's what it is. Pi a and the Y coordinate 2a, okay? So that makes sense, right? Kinda, a little bit, barely. Okay, all right. Now, when theta equal 2 pi, you've rolled all the way around now. So obviously your X is going to be 2 pi a, because you've gone one complete revolution and you're back at the bottom, and your Y is back at 0 again. So your X is increasing. It's not linear, though this almost implies that it is. The Y started at 0, went up to 2, and came back down. Okay? So without straining the old gray cells too badly, let's just see what it looks like here. Okay. You started with this, here's the point P, that started down here at the origin. So roll the circle back until P is at the origin. And as the circle starts rolling that way, it's over here at some point between theta is your parameter, and what you've done when you started here and rolled to there, you're rolling your theta is going from 0 past pi halves to, and here it's pi a. So you're somewhere in the first or second quadrant, real near the boundary of that with your theta here. You're in the second quadrant with theta. You see, you pass the pi halves and you've gone past pi halves. Okay, so there is that. Where you get all the way to here, the point that started here has rolled up, is now on top, and that's the maximum it'll ever get is 2a, because after that it's going to start coming down. Okay, so when it gets there, you're going to be at pi. The theta will be at pi, and the Y value is at 2a, of course, and the X value is half of a. You started here, and by the time you get there, you will have rolled over exactly half the circle, okay? And that would give you circumference of the whole circle would be 2 pi a, so this would be half that, would be just pi a. And then when you get on to here, your circumference, you roll it all the way around. This is 2 pi a, and you're back to 0 here. And then 3 pi a at 2a, 4 pi a at 0, and you keep going. Okay. So, your parametric equations, and I wish I had the motivation to explain all this to you. When I get to cycloids, I say just here are the equations, go with them. Flow, go with the flow here. You can kind of see why this is true just by some of the points that we know, but the x is just by just picking these points, you can't pick out the pattern very well. But if you were to do a better analysis of it, your x is a times theta minus sine theta, which is a little bizarre. An angle minus is a trig function of the angle, whereas your y is 1 minus sine theta, cosine theta, and that makes perfect sense because this is just a number and it goes between, in this case, between 0 and 1, even though it can't go to -1, but then you're just adding to that. In the first quadrant, this starts at 1, so you're starting at 0 here, and you're increasing till you get up here to theta equal pi. And what cosine has done was decrease that whole time, and then it starts increasing again, and that's where you start the other loop here. Okay, so that is a cycloid. Flip it over. Okay, yeah, cycloids have some value, I guess, okay, the way they are. But flip them over, and you've got something much more common. Have you ever noticed the wires between power poles? They have a dip to them. That, with the proper parameterization, can be likened to a cycloid. Okay? You can't help but have a dip in them. No matter how tight you try to put the tension on that, you're going to have a dip in them because gravity is always pulling down on the center of that wire. So it's going to sink, even if it means bending the poles. And it will do that. It will literally, if you were to be stretching those wires on the hottest day of the summertime, and you were trying to conserve as much wire as possible, you stretched them as tight as you possibly could between each one of those power poles, and then when winter came along, and the temperature started dropping, pop, pop, pop go the poles. The contraction of that little bit, metal doesn't contract a lot, but that little bit would pop those poles like crazy, okay? So you have to have that cycloid shape to it. Flip it over and you'll see that. And there are other things that will come out of that as well, okay? Now, things to note here, these equations are differentiable up to the cusp. They're nice and smooth and rounded all up to here, but then they have a cusp. And then they have a cusp. So you can differentiate, later integrate, do whatever you want to these between the cusp, but you can't differentiate at the cusp because this is approaching the negative infinity as a slope here, and this starts off a positive infinity there. So no way, never the twain do meet. So you're only there. Between the points, the cycloid is definitely smooth. And at the bottom of that section, let's see. I guess I missed the problem here. Oh, there it is. Determine the curve traced by a point P on the circumference of a circle of radius A, rolling along a straight line. Such a curve is called, okay. So they do all this leading up to it. And okay, from this figure, I love it when they say this. from this figure, you can see that this angle is true. Okay, here's the angle APC. APC. This angle right here, okay, that is a complementary angle, supplementary angle to this angle right here, and that's your angle theta. So a supplement means the sum is 180, so it's 180 degrees minus theta. Okay, this angle right here. And you almost ask yourself, so what? Okay, what's the deal with that angle? Okay. And since sine of theta is equal to sine of 180 minus theta, okay, now why is that true? Because, oh, well, it's true because you're in the second quadrant, and the sine of an angle in the second quadrant is the same as it is in the, well, not, okay, of 180 minus that. In other words, of the reference angle. The sine of the reference angle for theta is going to be the same as the sine of the angle for theta. So this has to do with just the sine being the same value. But you see, when you're pi 6 over here, 30 degrees here, 180 minus 30, same sine value. Okay. The sine of APC is, and here they give it in terms of 2 line segments. So let's go back and see what line segments we're talking about. The sine of this angle here, okay, APC wasn't it? Whoops, wrong way. Yeah, the sine of angle APC. So this angle up here, the sine of this angle here is this is theta here. Subtract pi halves from theta, and then subtract that because they're supplementary angles. 180 minus that, okay, which is subtracting a lot of things from a lot of things here. We were going to see what those line segments were. The sine of this angle here is opposite side over hypotenuse. So hypotenuse is A, okay? Well, this is AC over A. Remember, A is your radius here. But it's also BD over A because BD and AC are exactly the same length. So it doesn't matter which one you use. So that's what they were doing there, AC or BD over A. Now the cosine of that angle okay. Let's go back here to the cosine of the angle theta. Here's the angle theta. And the cosine of this angle theta is the, there's the hypotenuse still, A, and the cosine of this angle theta will be the cosine of it's going to be minus because the angle is obviously in the second quadrant. There's 0 to 90 would be the first quadrant. You're in the second quadrant. So it's minus, I can't breathe. Man. The cosine of this angle is this length here, okay? That's AP, okay? Over A. Little a is the radius, capital A is the point right here, so don't get those two A's confused, okay? And back here and see what they're saying with it. Cosine is minus the cosine of 180 minus theta, because number one, you're in the second quadrant, so it's the negative of the angle, and 180 minus theta, that would be this part here, and the cosine of this would indeed be that, only it would be the opposite of that, because the cosine of this angle theta is a negative number, okay? We don't want a negative number, we want a positive, so it would be minus that. And that would just be AP over minus A, okay? Which implies that AP is equal to minus A times the cosine of the angle theta, and that BD is equal to A times the sine of theta. So AP is minus A cosine theta, and BD is A sine theta. That was from the previous slide. Okay. Now, because the circle rolls along the x-axis, you know that OD is the arc length. That's what that stands for, though they haven't defined it for you, of PD. Okay, let's go back and see what they're talking about there. OD, which is the arc length from here, the length from here to here, that's the radius, or A. No, this D isn't quite an A yet. It's just OD then. And the arc length is the O to P in the arc length. Distance is just a linear distance. The arc length is a curved distance. Okay. And that's equal to A theta. Okay. Now we know that because arc length is equal to radius times the angle in radians. Don't ever try to calculate the arc length using degrees. Get the degrees to radians, then do it that way. Don't ever use degrees. Okay? Just about anything in calculus, don't do it. So, yeah, we've already, you can follow along and keep up with the angles, and they're doing that with their equations here of how far you've gone and you know, that type of thing on the with your. If you follow along in the text and in the book, and then on the slides, you'll see that is progressing at the rate they're talking about. So let's see what that is. Get it back up. Whoops, went too fast. All right. That's equal to A times theta. And that's arc length is equal to radius times the angle in radians. Okay. Furthermore, because AB is equal to DC, and that's equal to A, so let's go back and see. Whoops, too far. AB this is pretty interesting, okay? I would have started it the other way. No, it's rather strange. All right. I'm spending way too much time on this. In fact, I not even certain I agree with them on it right now. Obviously, oh, I know. Let's say AB is equal to CD. I'm sorry. We've already said that before. That's blatantly obvious. I was thinking they were saying BC. And I thought that's not even something you can talk about here. But AB is equal to DC. That is your radius. Okay? So, sorry about that. Whoops. Yeah. Because BA is equal to DC. I am saying that right, am I not? Yeah. I said AB, they said BA. Okay. And that's equal to A. You have X is equal to OD minus BD. Okay. X equal OD minus BD. Okay. Your X here is OD minus BD. That's your X value right here. OD minus BD. That's your X value. Okay? Now, BD is related to the sine of this angle up here. Okay? And the thing later. So, what they're doing is plotting this out for you. This is so awkward to go back and forth between this. So let's just stick to it. That's A theta, which is your total arc length, OD, minus sine A sine theta, which is that little bit you come back this way. And we saw that from before. Okay? Let's do it one more time. Okay. This is your arc length. Okay? But we've already determined, I went the wrong way, that OD is equal to that PD, that arc length, okay, which is A theta, because the circle rolls along the x-axis, okay? So let's go back. Yeah, thought I was going back, okay. So OD, see, this point right here started here. And as it's rolled along, okay, this is the distance it went, OD, and that has to be the same as this here, because this is the distance that you traveled here, that this point, if you flatten this part out right here, you would have OD is equal to the arc, and that's A theta. I know y'all are interested in this, right? Okay. So that's where they got that statement, minus A sine theta, which is that subtraction we just did. We said that is related to the sine of that. So there's your X value. The Y value is then the BA plus AP. Now let's see. This one should be a lot easier. The Y value here is BA plus AP. There's your Y value. Well, this is your radius, A, okay? And then this has to do with the cosine of this angle, okay? So that's how you get these two parametric equations. X is A theta minus A sine theta, whereas Y is equal to A minus the A cosine theta. That's where those two equations come from. La, la, la. Okay. So the parametric equations are these. Y is equal to A times theta minus sine theta. And X is equal to that. Y is equal to A times 1 minus cosine theta. Those are your parametric equations. And the cycloid in this figure has sharp corners called cusps. We talked about that already at the values 2 n pi A. And notice that the derivatives at those places are derivatives of theta, x prime, and y prime are both 0 at the points for where your 2 pi theta, and 0 over 0 is sometimes indeterminate, but in this case, not defined, okay, because they're neither one of them. That will not be a smooth continuous derivative at all means. So x as a function of theta is A times theta times minus sine theta. Y is A times 1 minus cosine theta. X prime is I would prefer this as A theta, and derivative of that with respect to theta would be A, and this would be A minus A cosine theta. Derivative of A sine theta is minus A cosine theta. And when you're at 2n pi, your cosine of that is always 1, and that would be A minus A is 0. So that's 0. This one, when you take the derivative, you just get 8 times the sine of theta. It's a minus here, and the derivative of cosine is minus sine, so that makes a minus plus. And then sine theta, everywhere 2n pi, it's also 0. So both of these have zeros. The parametric equations have that. Now, between those points, the cycloid is smooth. At the points, undefined. I mean, very short. Constant. Here's the definition of a smooth curve. We say it's smooth. Here's what we mean. Curve C represented by y is equal x equal f of t, y is equal g of t on some interval I is called smooth when the f prime, the derivative of that with respect to t, and g prime, number two things, are both continuous on I and not simultaneously 0, except at possibly the endpoints of the curve of the interval I. The curve C is called piecewise smooth when it is smooth on each subinterval of some partition I, not necessarily at the junctions. These are not. Okay. Now, they really too much to tell here. Now they're going to talk about the tautochrome and the brachistochrome. I never can say that very easily. Okay. And on this page, they show a picture of a handsome dude named James Bernoulli. Now, if you haven't gotten the paper topic yet, hint, hint, here's a couple. James Bernoulli, he was the older brother. He is also called Jacques Bernoulli, if you check on that, because Bernoulli is a very Italian-sounding name. Jacques, however, is a very French-sounding first name. Well, guess what? They lived in Switzerland, okay? Well, Switzerland has French-speaking Swiss, German-speaking French, Swiss, and Italian-speaking Swiss. They're right at the juncture of those three countries. So you have, in fact, Lake Geneva, that's in the French end of it. Lake, I don't know what's the other one. Very German-sounding name is over here. I don't know if there's a lake on the Italian part, but just about everything is all jumbled up in the thing. So Bernoullis were an incredible family, incredible mathematicians, incredible scientists, some of the very tops in the world at that time. Okay, so younger brother John, there's another potential paper topic. He was one of several accomplished mathematicians of the Swiss Bernoulli family. I don't remember which one, James or John, had a son, Daniel Bernoulli. Bernoulli's principle in physics, that by which jet planes can fly, or any plane can fly, Bernoulli's principle, what gives it lift. They're just all over the place. They're fantastic mathematicians and scientists. He is, they say, has a very prominent place at the early development of calculus. Now, with this bright of a family, okay, some of the brightest in the world, I don't know what your thoughts are. They didn't get along too well, okay? They were competing with each other. And it may have been Daniel, I don't know if it was or not, but one of the fathers, James or John, one, there was this big competition they had in Europe about every year or every so often. And He just knew he was going to win because he was top of the field, you know. The problem came out. He worked it up, solved it, submitted it, and then he found out he didn't win. He came in second. The son won. He kicked the son out of the house. Okay. All right, if you win, you're out of here. And so that's the type of family they were. Really functional, of course. Okay. Now, they talk about the tautichrome and brachistochrome, and these are really interesting concepts. You can follow it. I don't want to go into all the details here, and it's a pretty famous thing, and it's not a trivial thing. I'll let you read that, and if you want to write a paper topic on one or any little piece of that, you certainly can. Let's just go to the homework exercises. You can do any of the odds 5 through 21. They're all at calcchat.com. 13's at CalcView. You can do any of the odds 23 to 33. They're all at CalcChat. 25's at CalcView. You can do either 35 or 37. They're both at CalcChat. Either 39 or 41. They're both at CalcChat. Any of the odds 43 to 49. They're all at CalcChat. Either 51 or 53. They're both at CalcChat. 53's at CalcView. Either 55 or 57. They're both at CalcChat. 55's at CalcView. Any of the odds 69 to 65. They're all at CalcChat. Okay, and you'll see some other names in here that you might want to pursue, or what they were talking about. Number 65 talks about the witch of Agnesi. I don't know if that's how you pronounce her name. Very unfortunate. There was a translation error. I think she was Italian, and when you got either in the Latin to translating to English or to German or to something else, they used a very similar word, but not quite, and they came out witch rather than whatever the other one was. And since she was a woman, they decided to go with the witch part. So it was just, sort of like you wrote in your paper, how little respect. She was a brilliant mathematician, very unusual for that time for there to be such a brilliant mathematician who was a woman. And they named her curve a witch. Okay? And then they named the folium the Descartes. So there's another potential paper topic. But anyway, those are 59 through 65. They should be there. There's exploring concepts, 67 or 69. They should be at CalcChat. Then there's 71 or 73. They're both at CalcChat. 75 should be at CalcChat. There's a couple of true false, 77, 79. They should be at CalcChat. 81 should be at CalcChat. That's a baseball problem. And then there's a special project if you want to do anything on cycloids. They're there. And basically it looks like they had an etch-a-sketch. No, what did they call those things? Not etch-a-sketch, but those things that made you put a pin in a hole and did it around the circle and you got, say again? I think I know what a compass is. That just makes a single circle. But this was a game, a thing they made. You could make beautiful designs with them. I can't think. It wasn't Etch-a-Sketch, but it was something like that. But it looks like they did that, making some of these pretty designs. Okay. So let's move on to, tautichrome and brachistochrome problem. I'll just hit what we've got here. We won't go into detail. I forgot that they had it on the slide. Cycloids are related one of the most famous pairs of problems in the history of calculus, so we're not going to do it. Okay, the first problem, called the tautichrome problem, began with Galileo's discovery that the time required to complete a full swing of a pendulum is approximately the same whether it makes a large movement at high speed or a small movement at low speed. Now, what do they mean by that? If you were to take this pendulum here and raise it to B, and the time that it took to go from A to B and B to A, would be the same as if you only raised it here and it just went back and forth between here and C. The time would be the same. Why? Because when you raise it here, it's going to go faster. When you raise it here, it doesn't go as fast, but it'll make one swing in about the same time. Okay? The time required to complete a full swing of the pendulum, starting either from C or from A, either one is going to be about the same thing. Because C is not going to go as far. It's going more slowly, but it won't go as far. A to B will go faster, but it'll go a longer distance, but the time is going to be the same. Galileo discovered that. I don't know if he fully described it, but that was the tautochrome problem. I don't know if taut means your string or your line is taut, is stretched. I don't know where the name comes from. Chrome means time, okay? Chronology, the time is the same. Galileo realized that he could use this principle to construct a clock, and that's why you have pendula and clocks. It doesn't matter how big a swing you do, one complete cycle is going to be the same time. However, he was not able to conquer the mechanics of the actual construction, so he wasn't quite able to do it. Christian Huygens, on the other hand, was the first to design and construct a working model of this. There's another potential paper topic. He realized the pendulum does not take exactly the same time as complete swings of varying lengths, but awfully close. But in studying the problem, Huygens discovered that a ball rolling back and forth in an inverted cycloid, remember the cycloid was like this, I said flip it over, does complete each cycle in exactly the same time. Okay? Problem with the pendulum was that it was on a circle, because that's a radius. A cycloid is not the same as a circle. So that was the problem. As long as you keep the angle small, it's approximately the same. If you get too big of an angle, you start introducing some error. But a ball rolling back and forth in a tautochrome, in an inverted cycloid, will be the same time. And Huygens discovered that. Second problem posed by John Bernoulli, that's why he showed up, but that was his brother. This is John. In 1696, it's called the Bacchistochrome problem. In Greek, Bacchus means short, and chronos means time. So the problem is to determine the path down which a particle will slide from A to B is the shortest time. Okay? And now he did it along a inverted cycloid again, passing through A to B. The inverted cycloid is the path down which the ball will roll in shortest time. If you had a perfectly circular arc, it'll take a little longer if you go from the same 2 points. Any other shape, the shortest time will be this Bacchistochrome, which is the reverse, the inverted cycloid. Okay? The amazing part of the solution to the Bacchistochrome problem is a particle starting at rest from any point C on the cycloid between A and B will take exactly the same time to reach C. It's sort of the same thing as before. If you release it at A, it's going to reach B at a certain time. If you release it from C, it's going to reach B. And this was going back to the tautochrome problem that we were talking before. It's the same, okay? So it doesn't matter where you released it from, it will be the same. Of course, you can't release any further because that's the cusp right there. That's the maximum. Okay. So was there any calculus? Well, a lot of calculus in that. We didn't do any of it, thank goodness. In fact, I probably spent way too much time on it. All right, I've already given you the homework exercises. Let's go to, do we have time? How are we doing on time? Yeah, plenty of time, right? Okay. 10-3. Goodness, my throat's hurting. I'm sorry. I hope I'm not catching a cold. Whew, it hurts like crazy. All right, so you just noticed we were dealing with the baseball player in one of those examples before. So let's now go to 10-3, parametric equations and calculus. Oh, I thought that's what we were doing. Find the slope of a tangent line to a curve given not by a equation y is a function of x, but by parametric equation. Find the slope of a tangent line. Find the arc length of a curve given by a set of parametric equations, and find the area of the surface of revolution in parametric form. Okay? We've done all those problems before in Cal 2 probably. Now we'll do them in Cal 3 on parametric equations. So let's start with slope and tangent lines. Consider the projectile represented by the parametric equation x is equal to 24 times the square root of 2. I don't like this. That's the square root of 2. The square root is right there. T is outside the radical. Just glancing at that, you might think it's inside. It's not. It's outside. So when I'm writing this, I write 24t times the square root of 2. Keep that square root out there. Remove all ambiguity. Okay. And y is equal to minus 16t squared plus same thing, 24 root 2t. I would write that 24t times root 2, as shown in this figure here. Okay. These are parametric equations, x and y, in the parameter t. You know that these equations are enable you to locate the position of the projectile at any given time t. Give me a t, I'll tell you the x. Give me that same t, I'll tell you the y. Okay? So this will locate both of them. So the pathway would be that set of all the x and y coordinates up to here. Okay. You also know that the object is initially projected at an angle of 45 degrees. I don't know if you knew that or not, but when you see the square root of 2 in there, and you figure x is related to cosine and y is related to sine, yeah, that ought to give you a pretty good clue. 45 degrees is there because root 2 over 2 is there, both of their, the trig functions of that, okay? Now, if that was the case, which it is, and the slope m, which is equal to tangent of 45, and that's equal to 1. Okay. I'm having a little bit of problem with that because the way they're stating that, that's always 1, and it's not. Okay, it's 1 right here at t is equal to 0. But you can't say that's true of every value. Oh, is initially projected. Okay, I was going to say initially projected at an angle of 45 degrees. The slope of m at that initial move. That's all they say. The slope here is 1. Okay. Not anywhere up there. I thought we were showing there. I said, no, it's not 1 up there. It can't be. Okay. Initially at 1. Okay, got it. So how can you find the slope at some other time? We should have gone to this slide, then it would make sense. The next theorem answers this question by giving a formula for the slope of a tangent line as a function of t. Okay? So if a smooth curve C is given by the equation x equal f of t, y is equal to g of t. Okay? Both of those are good, smooth, continuous functions, all that kind of stuff. Then the slope of C at any point x, y is, hopefully this will seem like it makes sense, dy dx would be the same as dy dt over dx dt, right? Looks like those two cancel out and you get this, okay? Looks like that anyway. As long as, of course, this dx dt is not equal to 0. Because you can't do that if it's 0. But if that's not 0, that's it, right there. So if you know your x is a function of t, take its derivative. If you know the y is a function of t, take its derivative. And then do dy dt divided by dx dt. That will be slope at any point. Hey, that makes pretty good sense, doesn't it? Okay? So let's do it, if it makes that much sense to you. Okay. Find dy dx for the curve given by x equal sine t, y is equal to cosine t. How would you approach it? First, get my pen turned on. Okay, next. What will you do next? Anybody? What's the Jesus answer in Cal 1? Take a derivative. We'll do dx dt. Now, for those who haven't been in my class before, you know what I'm talking about there? You haven't? Okay. I give this dumb example, and I've been in several churches, different family members, whatever, in different places we live. And anytime they have children's church, and all the kids go up to the front, and usually one of the pastors or leaders or something will get there and start by asking them some question. Of course, the kids are scared to death, and they just sit there and stare at each other. And then finally, one kid will get the thing. He'll say, Jesus, because he figures in church, if you answer Jesus, they say, no, that's a wrong answer. They know you're always safe or pretty safe with that. So whatever they ask, some kid is usually going to say. So that's why I say in Cal 1, what do you think you'll do first? I say, what's your Jesus answer? For Cal 1, it's take a derivative. Okay, that usually works. Not always, but it will. That works here. What is your dx dt? Cosine t. And what's your dy dt? Negative sine t. Okay? So what's your dy dx? That would be dy dt over dx dt. Just like the symbols look like, they would say, that would be minus sine t over cosine t, which would be negative tangent t. Perfect. That's tan. I didn't separate my t from the... Okay. Okay. Negative tangent t. All right. Let's clear my scratch out of the way and see what they get. dy dx is dy dt over dx dt, so dx dt is minus sine t. dy dt is that's minus tangent t. Yep, right there. Okay, did anyone need that up a little longer? Okay. Now, okay. Because dy dt is a function of t, dy dx is a function of t, you can use theorem 10.7 repeatedly to find higher order derivatives. They just get a little messier is all, okay? d2y dx squared would be d by dx of dy dx, but dy dx is well, they're skipping a lot of steps here. It's d by dx. Okay, dy dx we know is d by dx of dy dx would be d by dx of dy dx. I mean d by dt of dy dx over dx dt. Now, that doesn't look like you're quite being fair about it, but you really are. That's your second derivative. And then your third derivative would be the derivative of this thing with respect to x, but this thing right here is that thing, okay? So that would be d by dt of this thing right here, and then again you divide by dx dt. Now, they don't give a lot of explanation here, but this is what the results turn out to be. to me, it leaves a lot to be desired, but they just leave it like that. So they're skipped example 2, so let's go back and find some space to do example 2. I think this will be the best space we got. All right, what are we doing on time? Okay, we go to 2:10, don't we? Yeah, okay, we got time. I think we can get it done. For the curve given by x is equal to square root of t, and y is equal to 1/4 t squared minus 4, I believe is right. Yeah. And this would be for t greater than or equal to 0. It should go to infinity. Keeps on trucking. Find the slope and concavity. Now, we'll have to remind ourselves, what in the world is concavity? Anyone remember that? Okay, whether it's cupping up or cupping down. Okay, what is that related to? Second derivative, exactly. Okay, slope is related to the first derivative, the concavity to the second derivative. And we want to find both of those at the point 2, 3. Okay. Now, those are XY points, 2, 3. If you're going to find the first derivative, I'm sorry, find the slope, what do you got to find? First derivative, I'm sorry, gave the answer. I would not suggest trying to do it in that form. What form would I suggest? T to the 1/2. Never use radical form, always get an exponential form. So now we're looking for x, I'm going to write it out, dx dt. Okay, what would that be?
T to the negative 1/2.
Exactly, okay, which you could write as 1 over 2 times the square root of t, if you prefer that for calculational purposes. Okay, how about dy dt? Times 1/4, right? And 1/4 of 2t would be, yeah, 1/2 t, t over 2, okay? T for 2, okay. Now, at the point, okay, what's the slope then? Yeah, is dy dt over dx dt. Okay, and that would be t over 2 over 1 over 2 root t. Okay, but we're wanting this when x is equal to 2 and y is equal to 3. Well, how can we get this? When x equal 2, what is t? 2 is the square root of t. What would t be? It's, okay, this is your xy pair, right? So x equal 2, what is t going to be? X is the square root of t, so if 2 is the square root of t, what's t? 4, right? Okay. Now, it better work. It doesn't work. Okay. No, it does. Okay, wait, yeah, it does. I think it does. So let's see what happens if we put a 4 in for t here. Y is equal to 1/4 of t squared would be 16 minus 4. That would be 12, and 1/4 of 12 would be 3. Yes, that works. Okay, that point is on the curve at t equal 4. Okay, so if we want the slope at that point, that'll be when t is equal to 4. So the slope when t equal 4 will be, what would that be? 4 over 2 over 1 over 4. 2 times 2 is 4. So let's see, I'm just going to wipe out one of those sets of 2's, and I'm going to be left with 8. 4 divided by 1/2 is the same as 4 times 2, so that slope would be 8. Pretty steep there, okay? And indeed, if you look at your book, you see that is really steep there, okay? Now that was your first derivative. We also need to know the second derivative, d2y dx squared, and there we're going to have to look at the formulas we just did. So I don't have much room. d2y dx squared, that's going to tell us something about the concavity at that point. T is equal to 4, remember, okay? And we know this is, okay, first, let's clean this up a lot, okay? The dy dx, I didn't do it before because it was really easy to plug in. This is going to be t over 2 divided by this, which is times 2 root t over 1. The 2's go out, and this is t to the 3/2, right? 1/2 times, yeah, t to the 3/2. There's your dy dx. And let's see if it works. If you cube, let's take a square root of, square root of 4 is 2, cube that, and you got 8. Yeah, that works. So your d2y dx squared, which we just had in the boxes, is the same as d by dt of dy dx divided by dx dt. Okay? Or our dy dx was this one right here. Nope. dy is this one right here. So this will be d by dt of t to the 3/2 divided by dx dt, which we already did. That was this one. Okay? So what is d by dt of that? We can do that, can't we? This one right here. Please say yes.
So that would be 8 to the...
All right, 3/2 t to the 1/2, right? You're taking the derivative of this thing. Okay?
So it was
Power rule.
okay.
3/2 t to the subtract 1, or 2/2 from that, you get 1/2.
I was confused on what the word.
Yeah, I just realized you got the root of 3 over 2 with this 3/2.
Yeah, okay. All right, so that's the numerator part. Our denominator part, again, was this ugly little thing down here, which was 2t 1 over 2t to the 1/2. Okay? So this would then be, if you flip that over, in fact, I think I'll do that, that'll be times 2t to the 1/2 over 1. And t to the 1/2 times t to the 1/2 is t. And the 2 will go in this. That would be 3t. And what was our t? No, t. 4. So this will be 12. Now what does that tell you about concavity? Concave up. Because the positive concavity is concave up, negative concavity is concave down. Okay. That's greater than 0, so it is concave upward. That's all they were asking for there. Have we run out of time? I believe we have. Sorry about that. We'll start next time on a curve with 2 tangent lines at a point. That's the example 3, top of page 712. Oh. Yeah, okay, yeah. And, in 10.3, we got pretty far along. Do either 5 or 7. They're both a calc chat. 5's a calc view. Do any of the odds 9 through 17. They're all a calc chat. 13's a calc view. And I think you can stop there. We'll do the rest of those later. Good deal. You too. Thanks.